So now hopefully most of us are familiar with the ideas of flux and divergence for any old vector field already. Now let's start to talk about more specific fields that we have in physics. And firstly, we're going to talk about electric fields. Before we get into electric fields, let's actually discuss electric force. So we might know about this thing called charge, and particles might have positive and they might have negative charge, or they might have no charge at all. That's also possible. Now, if you have two particles of different charges, one have a positive charge and the other have a negative charge, then the force acting on these particles will tend to attract these two particles to move in to each other. Whereas if both of the charges are the same, they're both negative or they're both positive charges, then there'll be forces on the particle which acts so that the particle seems to repel away from each other or wanting to move away from one another. Now, you might have also heard of this thing called Coulomb's law before. Coulomb's law basically says that the magnitude of these forces depends on only two things. They will depend on the amount of charge each particle has, and also depend on how far the particle are away from each other. To be more mathematically precise, the force will be proportional to the size of the two charges and will be inversely proportional to the distance between the two charges squared. The second one has got this really catchy name as well, called the inverse squared law. So now let's be a bit more specific. Let's only consider the force acting upon this charge here. We'll say that this charge is the charge we're considering, and we'll say the other charge is just a charge that just happens to be there and exerting a force on our dummy charge that we want to look more into. So if we want to work out the force that's being exerted on this particle, we can use Coulomb's law. And the force, the magnitude of the force, will be equal to some constant multiplied by this charge, multiplied by this charge here, divided by the distance between these two charges squared. And we know that force should be a vector because there will be some sort of direction involved with which direction the force is acting on. And so for this case, the force will be acting that way, and so the force acting upon this particle should be some sort of vector quantity, hence I'll add this unit vector at the end here, where the unit vector will be pointing in the same direction as where our charge is with respect to the origin. And because our unit vector has got a magnitude of 1, it doesn't actually affect the actual magnitude of our forces at all. So this bit here is the magnitude of our force, or how much of the actual force there is, and all our vector is doing is just saying which direction the force is acting at. And the equation that we have coming from Coulomb's law will be correct for the example that we have. Wherever I move this arbitrary charge around, the equation for the force will still be correct. But sometimes it's not the most useful thing to know the actual force of this particle at whichever location we want. Because, you know, this charge that we have is sort of arbitrary. So whatever information we get about the electric force should sort of be independent of our arbitrary charge, so that it's a bit more useful. So we don't actually have to consider about this arbitrary charge to get the general idea of the electric force in our area. So this is what we could do. We could look at the equation for electric field again, and we'll just take this arbitrary charge out of the rest of the term. And this bit here could be defined as something else. And this will be what we call the electric field. So what exactly is this electric field thingy that I just introduced? Well, let's say our arbitrary charge has got the charge of 1 unit, or if you want to be more precise, 1 Coulomb. Then the electric force at any location would just be the same as the electric field. So we can sort of define the electric field as the force that will be acting on a particle which has got the charge equal to 1 unit, or a unit charge if you want to call it that way. And the actual force acting on the particle at any location will just be the electric field at that particular point times the size of our charge that we have. As we can see, the electric field here is independent of the size of our arbitrary charge. And so really, if we think about it now, electric field is much more sensible thing to think about than compared to the actual electric force itself. And electric fields is just one of these vector functions that we've been discussing earlier. So of course we can do most of the maths that I've mentioned in the past 2 videos on it. Now the idea of electric field might be new to some people, but to a lot of you might have seen it before. You might have seen diagrams looking like this one. Now you might have seen this one and realize that it doesn't really look like the vector fields that I've shown you before. And the only reason that it doesn't look like so is because what I've done instead of just showing all the vectors individually is they've connected up all the vectors to form the different lines, as you can see there. Now when you see diagrams like this, it will still convey pretty much the same information as diagrams looking like this. However, the direction of the field now just sort of follows the field lines, and the magnitude of the electric field at any position will just depend on the density of the lines at any particular location. So if you were to have something like a positive charge, its electric field would be going this way, whereas we have a negative charge, its electric field would be going in the opposite direction towards the charge. And if you think back to the definitions of electric field, that you're using a test charge on it, a positive test charge, then you sort of see why the field lines will have to be going this way.